All right. Are we ready? Less enthusiastic. Are we ready? I said less enthusiastic. Okay, now more enthusiastic. Are we ready? Now you make me feel like I'm a rock star. Thank you. Always wanted to do that. Okay. We left our previous lecture with the dependent functions, and I give you this slide for a very short recap what we're doing. We are listing the rules for pi types, the rules for the dependent function types. And we did the formation rule. They told me the clicker thing doesn't work well, so I hope, do people see this mouse? Yeah. So we have the formation rule and the introduction rule and the elimination rule. So this is just how we form types. This is the lambda, and the elimination is the evaluation. And then we still have to do the computation rules and the competence rules. Okay. We did this, and we left off with how is this evaluation? Well, it is evaluation if you carry it out with substitution, and then it looks like what you would usually say when you evaluate a function that you evaluate it at a point. And in this case, we evaluated it on the point 2 of natural numbers, which is the successor of 0. Okay. And then, actually, yes, evaluation respects judgmental inequality. There is a congruence rule, but you can read it in the textbook. Okay. Computation rules. We have the computation rule called beta that already Brigitte told you about. So what does it say? Do we remember? It was local soundness or completeness. One of those. The one was local soundness. Yes, very good. Local soundness basically saying that if I, if I have a lambda abstraction of y, and then b of y, and then I evaluate it on x, this computes, right, to substitute y for x, b of x. And this is the computation rule. So basically, it kind of looks like the evaluation rule, right? It basically tells us if I have a lambda, and then I have a constructor first, the lambda, the introduction, the constructor, and then I have the eliminator, so to say, the function application, the evaluation. Then I'm getting basically the same thing back as I did initially. Okay? And this is what the beta rule is supposed to say. And there's the other one, the eta rule, that says, if I have a function f, then if I do lambda x, f of x is the same as f, right? So here I first have the elimination rule, right, the evaluation on f, and then the constructor, lambda, and this has to give me the same thing, right? So in the beta rule we had constructor first, eliminator second, and in the eta rule I have the eliminator first, and then the constructor. In both cases we should get the same thing. I will talk a little bit more about these two rules and how they look like in rock. But essentially, I just want to make a little side note about the eta rule. And in the context of the meta theory, right? When I'm saying there can be many type theories, and there are ways to present them, and they have computation rules. The beta rule, the reduction rule, so to say, the computation rule, is usually present in that form. So usually what you want to do is kind of morally having a constructor and then an eliminator. But the eta rule is actually interderivable with something you call an extensionality rule. Okay? And an extensionality rule is basically telling you, maybe I can actually write it down. An extensionality rule will tell you how do I derive that the two functions are equal. What premises do I need to say that two functions are equal? And usually they have to be well formed, that's the first, so F has to have the correct pi type and G has to have the correct pi type and so on. But basically what you want to say is, well, they are, in this case, judgmentally equal if they are equal at every point, right? I will get to your question in a second. So what you want to say is, here you want to have a premise that if for every x in A, f of x is judgmentally equal to g of x, that's type b of x, right? Then you can say that f and g are equal functions, and we call this an extensionality rule. Why am I mentioning this? It's because for other types that you can and usually do introduce in your type theory, that one comes more naturally, okay? And it behaves better when you have an equality checking algorithm, okay? And this extensionality rule is actually interderivable with the eta rule, with the second one here, in the presence of the computation rule beta and other rules that we saw so far. So this is an alternative way of giving this computation rule, so to say, right? But we don't think of this as a computation rule because you wouldn't really want to rewrite f or g, like they're both kind of, they're variables in a sense, right? They're not lambdas, so you wouldn't really compute away anything. Here at the top, you have a lambda, and then you have an evaluation, and you can kind of see what you want to compute here. It's just equality between two, so to say, with your meta, but variables of a function type. And usually, for the other type formers, that's, in my personal opinion, a more natural one. However, eta rule is super common, and I think historically it was there before the extensionality rule. So, and it's in the textbook, so that's why I included this one on the slide. But if we do some meta theory on the last lecture, if you ever read papers about that, the extensionality rule is the other side of the eta rule. Okay, there was a question somewhere there. Yeah.
I've been wondering if this is just convention, but in our first lectures we were talking about adding the types to our lambda functions or to our lambda terms, and are we just sort of obscuring the way that our lambda variables have types, or is that not important?
Aha. So if I understand correctly, you are referring to this lambda y having a dot and not colon a. Is that correct? Okay. We don't need to. Okay? And the reason we don't need to is because this term has a type here that will tell us, and here, you see in this context, we will know. So when we construct this function, it will have, inseparably, it will carry its type. And the pi type will tell us that this y here is of type A, right? What I'm saying now is not necessarily how people implement stuff in the proof assistant, okay? So this is a very good point, right? What people usually want to do is have some rules for which they say, oh, it actually preserves types, right? So then they just drop the types from the memory to make it compute faster, okay? And they sort of check that these types are preserved with whatever they are doing. This happens usually in the kernel of a proof assistant, when they are like trying to do stuff for you, basically. And sometimes you need to keep the type annotations, on the lambdas in certain cases so that this goes through. In this particular setting that we're doing now, I'm basically telling you that every time we have a term, we will know, right, what types of stuff are. And that's why we don't have to include the type annotation. Yes?
Sorry, I'm just having a bit of trouble wrapping my head around this. Do you happen to have examples the previous slides?
For the beta rule?
Yeah.
Yes. Okay. I didn't include one, and now it's biting me. Okay, so let's try with this one, right? So here we have the evaluation. Okay, so what did I have? So my lambda x, let's try. Lambda x, and then I have zeros, zeros, and these zeros are x times, and I do the same. Okay, so I first constructed something, and now I can evaluate it on, may I be lazy, on number 2, okay? This is evaluation, instead of a successor of 2, right? And this needs to be now judgmentally equal. Am I doing the correct thing? This should be now. That looks more like an evaluation than like a Vito rule, right? Okay, yes, question.
Maybe it helps if you write like x times under the bracket.
Yeah.
Then it becomes 2 times.
So I constructed and then I evaluated and I should get the same thing. Okay, let's try with the theta rule. Okay, I have a function f. Oh, that's the more tricky one, right? Because I want this f here to be symbolic, otherwise. So f here has to be a function, right? So I could do, okay, let's try it. Okay, so let's pretend that our f, and I'll write equals in quotes, is this lambda x 0, 0, x times. Okay, now I want to plug it in, and I want to have lambda y, lambda x 0, 0, okay, and then I want to apply this lambda to y, okay, and now this should be judgmentally equal to lambda x 0, 0, x times. Does that one make sense? Or are you even more confused?
Yeah, that makes sense.
Okay, so here, for this f here, now I instantiate it with a concrete function, which is give me x many zeros in a vector. Question?
Maybe to rephrase. So the first rule, the beta, basically does the substitution, right? The y can be anywhere within the b, and then we can replace all those y's by x. But in the second rule, we don't.
You're saying y can be anywhere with b.
In the beta rule,
Here?
in general.
So instead of 2 saying y?
And more like the way it's written, it looks like the eta rule allows us to do a substitution. But it doesn't, right?
No, don't think so.
Because in the beta rule, we do a substitution. And
Yeah.
yeah.
Okay,
The,
okay.
the beta rule is beta reduction, right?
Does it help if I
the beta rule is
write-
just beta reduction.
Yeah, actually,
Yeah.
no beta reduction.
Yeah. So, but the eta rule is eta expansion, I guess, in like lambda terms and stuff. Yeah.
I'm not sure if this is helpful or not. You have to tell me. Yes? Between expansion, reduction, and
Well, there's
So what we mean by eta reduction, right? I think what we mean is that we are going to rewrite this big lambda x f of x to f, right? And when we mean eta expansion is I have an f, I want to have something of this form, I can just rewrite it to the bigger way. So the difference is in which way I am rewriting along this equation.
And the same computation rule applies to both.
Well, yes, because if I'm going from here to here, I'm eta expanding the term, and if I'm going from here to here, I'm eta reducing the term, but actually it's the same equation, right? I'm actually, I wasn't really talking up to this point very much about the equations are oriented, because for us they're symmetric, right? So for the derivation themselves, they don't matter. When they do matter, when we say eta reduction or eta expansion, is when we're trying to implement stuff in the proof assistant and we're trying to compute with these equations, right? But for the derivations themselves, they just appear in the derivations, and either way is okay. If we want a symmetric version, we can just use the symmetry rule for the judgmental equality in this case, and we are done. Okay. Yeah.
If the rules are not oriented, how are we, I think I know the answer, but why is the vector designed this way? Because it doesn't automatically make us confident that the way the proof assistant writes these in an oriented direct where they're all reducing this and all apart. And there's a whole separate business of saying that that's equivalent to these unoriented equivalence relations. Why do we prefer it to be this way?
Because it's simpler.
Okay.
You can add orientation in which you want to rewrite stuff, all you want, but the equation still holds, right? You chose to rewrite in a certain way because it gives you some computational advancement that you like, right? But the reason that you could do it is basically these things are equal. And, for a non-programmer / a mathematician, when things are equal, it doesn't matter which way they're equal, right? You are allowed to choose a side if it's beneficial to you. You're allowed to not choose a side if it doesn't matter, right? Yes?
So just a notation question. So for the beta rule, we have b applied to x, for example, and then we have the lambda applied to x. So the lambda applied to x, I think of that immediately as there's some substitution happening. But with b applied to x, what's going on there?
Right. So this part here, this space here, is very much larger than this space here. Right? The correct way would be to actually not. So why are we using this notation? Is because it's what we're used to, right? This is the easiest way. When we apply function, we put the argument right next to it or in the parentheses, and that's it. Actually, this space here means the evaluation rule from here, okay? Whereas, where am I? Whereas this space here just means the dependency. Okay. I love that there was a whoa. Because this is your question, you were not the only one with that question. Okay. Does that clarify this rule better? So this b of x here and this b of x here just identifies that this is indeed a section, right? It's a dependent term, and it depends on whatever came in A. This thing here, this space, says I have a function and I apply it to x. Okay? So an even better way to say it would be evaluate my lambda blah 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 on x. Okay, I'll write it full. Now I'm introducing a new symbol called EV, right, for the evaluate. Okay, what am I evaluating? I'm evaluating lambda y, b of y, and this guy here is again just the dependency, see? And then I'm evaluating it on x, and this has to be judgmentally equal to
You write y for x.
yes, I wrote the substitution y for x.
X for y, right?
That's exactly right. So I will go back to the stupid notation because apparently I can't take the other one, but that means that b is now dependent on x, and here b was dependent on y. So this space here is dependency, and the evaluation now I have an explicit constructor called EV for evaluation that takes two stuff. One is the function, and the other one is what am I applying it to. So the beta rule is actually this one, right? Okay. Next. Dependent functions can also not really be dependent. Okay? So ordinary functions from A to B are a special case, and it's exactly the case when the codomain has no real dependency. Okay? So I have a small derivation here, and I have this derivation here because I want to introduce to you a new, let's call it symbol, but it's another structural symbol, and structural means that it can happen in any type theory, and it's really along the lines of this turnstile symbol and the type judgment and so on. And this one is introducing a definition, okay? So what I'm saying by this derivation, so how do we introduce new definitions in a type theory? Well, basically like this, right? So what I want to say is I have a derivation, so this thing above the last line is a derivation of a basically non-dependent type, right? It's a pi type where the codomain doesn't really depend on x here. So here I'm not missing the dependency, I'm saying it's really not there, okay? And how do I know that it's really not there? It's because of this premise here, right? B is a well-formed type in gamma without A being mentioned in the context, right? So B really doesn't depend on X. And then I can weaken this to B, still being a well-formed type in a weaker context. So we can add X here and then form a pi type with a pi formation rule, okay? So this is how we know that this pi type is well-formed if these two premises hold. And now what I can do is, anytime I have a conclusion of this form, so either a type or a term judgment, but not an equality judgment, okay? I can say I will define a new symbol, arrow, right, A arrow B, to mean exactly this, a pi type from A to B, okay? So in a prefix form, that would look like I have a function symbol, arrow, that takes A and B, and it is defined to be the pi type where B has no dependency. Okay? And this is how we would introduce, new constants all the time. Okay? If I have something that I've already derived and I want to name it, this is how I introduce the name. So what happens in the type theory morally, so this is a nice notation, right? But morally what you're doing is you're adding two new rules to your type theory, okay? A definition extends the type theory that you work with a new constant. So the constant for me would be the arrow, right? And the following two rules. So one is here how I introduce this constant. And the second one is what is this judgmentally equal to, okay? So I can allow myself this notation, but morally what I'm doing is just adding two new rules. And that's it, right? I'm introducing a new constant, and I'm giving it a judgmental equality to be the thing that the derivation is. Okay. Let's derive a function. Okay, now we have rules for function types, so let's derive one. And what's the first function you think of when I say, give me a function you want to derive? Identity, yay! There we go. So we can derive the identity type, and of course we're using the same definition style, right? Identity on type A is lambda XX from A to A, and of course it has an easy derivation. It is just the lambda rule and then the generic element or the variable rule, and we're done. Okay? The other function that you can derive is the composition function, right? So you want to derive the composition that is take two functions, right? And then compose them so that at every element you first apply f and then you apply g, okay? And this is not a dependency, this is not a function application. So, you know, it would be really easier if I just used the EV symbol, but then I couldn't screenshot the textbook and you would have two different notations and you would be even more confused. So it is what it is. How do we derive this? Do we want to try it or do we want to see the solution and walk through it? Try it. Ah, you shouldn't have asked. Should not have asked. Mistakes were made. Okay. So what we want in the end is to derive comp colon equals, what do I have, lambda g first? Lambda g, yeah. Lambda g, lambda f, lambda x, g, applied to f, applied to x. Okay? What type does this function have? Right? It's a pi type, or we can try with ordinary functions. Okay, so we have something. So we know from B to C, and then from A to B, and then from A to C. Yes. Did I write the type correctly? You're my type checker now. Good. Okay, what do I need? Some gamma, and I need A, B, and C to be well-formed types. Okay? How do I derive this? Well, this one was a definition, so this is really easy. So while I'm just writing the same thing without a comp colon equals, you can think about what the next step should be, and the last row will not see this because it's way too small. So bigger lambda f, lambda p, lambda x, g of f of x, type B to C, A to B, A to C. What is the next step?
Gamma, comma, G of type B to C.
Mm-hmm.
Turnstile, yeah, that.
Mm-hmm. The rest.
Yeah.
Lambda f. Can I write dot dot dot? Yes, I can. What is the next step?
Just continue.
Just continue, yeah. So G from B to C, F from A to B, turnstile lambda x, G of F of x. Okay? One more time.
Please write larger.
X of type A. What was the comment? I didn't hear.
Write larger. For the question.
Ah, right larger? Mm-hmm. Okay. Gamma, G from B to C, F from A to B, X of type A, G of F of X. Good. Of type C. Good. Okay. Now what? A is a type, yes, but what are we doing with this?
Like gamma does need to be type, but maybe that's there.
Okay. What rule are we trying to use? That's my question.
Evaluation.
Okay. What is the evaluation rule? Yes. Okay, so I have to say that F, yeah, I can't really write evaluation, can I? Because for evaluation, here has to be a variable, and here I don't have a variable, I have a term. I have a composite term, it's f of x. Beta. Okay, beta has a conclusion, an equality. So not going to work. Eta, also an equality. Not going to work. Yes, substitution. Good. So the problem was I want to have a variable here, but I have a composite term. So how do I get a composite term if instead of a variable I use a substitution rule? Okay, so I give myself g of y of type C if y is of type B, yes, and blah blah blah, the rest of the context. And what I also need is for f of x, the thing that I'm substituting it for, right, has to also have type B in the context without y. So x of type A and blah blah blah. Okay? Now we can do evaluation rule. Okay. Look, now I'm running out of space, so I will do the cheat sheet thing. Tuck, tuck. There it is. All right. So we reach. Okay, I'm using this. So the textbook is using this notation, right? So an arrow from B to C can be also written as C with the exponent B, just to make it shorter and fit onto the page. So we did all of these guys now, right? We did this, and then this is the substitution rule. So I introduced the y and the g of y, and then we can do the evaluation rule, right? And